Welcome to the Master Course on the Introduction to Security Engineering. Over the next several modules, we will embark on a journey from foundational principles to practical, hands-on tools, building a complete picture of one of the most critical roles in the digital world. Let's begin. Good morning, everyone. Welcome to today's session, Lesson 1.1, Introduction to the Security Engineer. Imagine a medieval kingdom. It has strong walls, watchtowers, and guards at the gate. Who designed those walls? Who decided where the towers should go for the best line of sight? Who ensured the gate was reinforced against a battering ram? It wasn't the guards who patrolled day to day. It was the royal architect and engineer. In the digital world, a security engineer is that master architect, designing and building the defenses that protect an organization's most valuable treasures, its data. By the end of this lesson, our objective is to define the role and primary responsibilities of a security engineer within an organization. We will explore their core mission and then break down their responsibilities into 4 key areas: designing, building, testing, and maintaining digital defenses. Now let's move into the core content. The primary mission of a security engineer is to proactively prevent security breaches by designing and implementing secure systems from the ground up. They are the builders and the architects of an organization's security posture. Their responsibilities can be broken down into 4 main pillars. First, design and architecture. Before a new network, application, or system is built, the security engineer designs its security framework. They answer critical questions like, how will we control access? How will data be encrypted? Where do we need firewalls? Their goal is to make the system secure by design, not as an afterthought. Second, build and implement. Security engineers don't just create blueprints, they also do the hands-on work of building the defenses. This includes configuring firewalls, setting up intrusion detection systems, implementing encryption protocols, and deploying security tools across the organization. Third, test and validate. A fortress is useless if you don't know its weaknesses. Security engineers constantly test their own defenses. They perform vulnerability assessments and penetration tests to find holes before attackers can. And finally, maintain and upgrade. The threat landscape is always changing. New viruses are created and new attack methods are discovered daily. A security engineer's job is never done. They are responsible for updating and upgrading security systems, responding to new threats, and ensuring the defenses remain effective over time. Now that we've laid the theoretical groundwork, it's time to solidify your understanding. We've mentioned that a security analyst is like a guard on the wall. They monitor for active threats, while the engineer is the one who designed and built the wall itself. This is a great one to try yourself. Here's your activity. Research and list 3 key differences in the day-to-day tasks between a security engineer and a security analyst. When you do this, you'll discover that an analyst's day is often filled with monitoring alerts and investigating active incidents, while an engineer's day is focused on designing systems, configuring firewalls, and writing security policies. The builder versus the guard. To conclude our lesson, let's move to a brief assessment. To really crystallize this concept, here's a prompt to consider. Here's your prompt. In 1 or 2 sentences, describe the main objective of a security engineer. What this reveals is that the main objective of a security engineer is to protect an organization's data and systems by designing, building, and maintaining a robust and resilient security architecture, aiming to prevent breaches before they happen. Lesson 1.2, the role of the security engineer. We've established that the security engineer is the architect of the kingdom's defenses. But what does that mean on a daily basis? They are actively inspecting the walls for cracks, upgrading the gatehouse locks, and training the guards on new defense strategies. Our learning objective for this session is to identify the specific tasks and contributions of a security engineer in maintaining an organization's security posture.
We will detail their day-to-day responsibilities, covering their involvement in system design, security tool management, vulnerability assessments, and incident response. A security engineer's contributions are both proactive and reactive. Their daily tasks are diverse and critical. First, they are deeply involved in security system design and implementation. When a new server is set up, the engineer is there to ensure it's built securely from the start, integrating controls like firewalls and VPNs. Next, they are the masters of the security toolkit, responsible for managing and maintaining security tools. This includes configuring and updating antivirus software, intrusion detection systems, and the SIEM systems that collect and analyze security data. They also handle vulnerability management, constantly scanning the organization's networks for weaknesses. When a vulnerability is found, they prioritize the risk and work with other IT teams to get it fixed. They also help write the rulebook for security through security policy and procedure development, creating policies for things like password strength and data handling. Finally, they provide crucial incident response support. While an analyst is the first responder, the engineer analyzes how an attacker got in and then builds new defenses to prevent it from happening again. To really solidify this concept, here's an activity to try. Here is your activity. Outline a typical day in the life of a security engineer, highlighting at least 3 distinct responsibilities. When you do this, you'll paint a picture of a dynamic role. For example, 9 a.m. might be a team meeting on new firewall rules. 11 a.m. could be running vulnerability scans on web servers, and 2 p.m. might be spent helping to write a new password policy. Excellent work on the activity. To conclude our lesson, we'll move to a brief assessment. A company is launching a new mobile app for its customers. Consider this scenario. Here is your prompt. Which of the following tasks would be a security engineer's primary contribution to this project? A. Monitoring the app for live attacks after launch. B. Designing the secure login and data encryption features before development begins. C. Answering customer support calls about the app. The correct answer is B. Designing the secure login and data encryption features before development begins perfectly reflects their core role in making systems secure by design.
Lesson 1.3, Qualifications for a Security Engineer. Welcome to Lesson 1.3. To become a master builder of digital fortresses, one needs a specific set of tools and skills. A security engineer needs a blend of technical knowledge, formal education, and hands-on skills to be effective. Our objective is to list the essential qualifications, skills, and educational backgrounds typically required for a security engineer position. We will cover 3 main areas: education and certifications, technical skills, and essential soft skills. First up, education and certifications. A bachelor's degree in computer science or cybersecurity is a common starting point. Industry certifications prove specific knowledge. Key certifications include CompTIA Security Plus, the Advanced CISSP, and the Certified Ethical Hacker. Next are the technical hard skills. A deep understanding of networking is crucial. You can't protect a network if you don't know how it works. Proficiency in operating systems like Windows and Linux is a must, as is knowledge of scripting languages like Python for automating tasks. Of course, hands-on experience with security tools and cloud security skills are also in high demand. Finally, we have the professional soft skills. The ability to analyze complex problems is paramount. Engineers must also have excellent communication skills to explain security issues to non-technical people. And of course, a sharp attention to detail is critical, as a single misconfiguration can create a major vulnerability. This is a great one to try yourself to see how these qualifications fit together. Here is your activity. Create a personal development plan, identifying 1 technical skill, 1 certification, and 1 soft skill you would like to acquire or improve. What this reveals is a clear path forward. For example, you might decide to learn Python.
study for the Security Plus exam, and practice explaining technical topics to a friend. To conclude, let's check our understanding. Here's a quick matching prompt. Here is your prompt. Match the qualification to its relevance. 1. Python scripting. 2. CISSP certification. 3. Communication skills. A. Explaining a security risk to the marketing department. B. Automating the process of scanning for vulnerabilities. C. Proving a broad understanding of security management. When you work through this, the connections become clear. Python scripting is for automating scans. The CISSP proves a broad understanding of security management. And communication skills are for explaining risk to other departments.
Lesson 1.4: The Importance of the Security Engineer. Welcome to Lesson 1.4. What happens when the kingdom's architect does a poor job? The walls crumble and the kingdom falls. The consequences in the digital world are just as dire. This is why the role of the security engineer is not just an IT job. It's a vital function for business survival. Our learning objective is to explain the critical importance of security engineers in protecting digital assets and ensuring business continuity. We will discuss their role in protecting assets, enabling business operations, and managing risk. First, security engineers are tasked with protecting critical assets. An organization's most valuable assets are digital, including customer data, financial records, and intellectual property. The engineer builds the digital vaults that protect this information from theft. Second, they are essential for ensuring business continuity. A major security breach, like a ransomware attack, can grind a business to a halt. By designing resilient systems, engineers ensure the business can continue to operate even when faced with threats. Finally, their work is about managing risk and maintaining trust. Customers will not do business with a company they believe cannot protect their personal information. Strong security engineering is a cornerstone of customer trust. To really bring this home, here's a chance to connect these concepts to the real world. Here is your activity. Write a short paragraph explaining the importance of a security engineer, citing a real-world example of a security breach that strong engineering could have prevented. When you do this, you might cite the Equifax breach. What this reveals is how a failure in vulnerability management, a core engineering task, can have catastrophic consequences, underscoring the vital importance of the role. To conclude, let's assess our understanding of their role in the bigger picture. Here is your prompt. How does a security engineer contribute to an organization's overall risk management strategy? A solid answer would state that a security engineer contributes to risk management by identifying potential digital threats and vulnerabilities, and then implementing security controls to reduce the likelihood and impact of an attack, aligning the company's technology with its tolerance for risk. Lesson 1.5: Important Terminologies. Welcome to Lesson 1.5. Every profession has its own language. To be a security engineer, you need to understand the language of cybersecurity. Learning these core terms is the first step. Our objective is to define key cybersecurity terminologies relevant to a security engineer. We will define and provide context for a foundational set of terms: threat, vulnerability, risk, exploit, and incident. First, a threat. A threat is a potential for harm. This is the who or what that could attack you, like a group of cybercriminals or a computer virus. Next, a vulnerability. A vulnerability is a weakness or flaw. This is a flaw that a threat can take advantage of, like outdated software or a weak password. This brings us to risk. Risk is the potential for loss when a threat exploits a vulnerability. It's the intersection of a threat and a vulnerability. For example, the risk of data theft exists because a hacker, the threat, could exploit a bug in your website code, the vulnerability. An exploit is the specific method or code used to take advantage of a vulnerability, like a specially crafted email that runs malicious code. And finally, an incident. This is a security event where an attacker successfully exploits a vulnerability, resulting in a negative impact. It's when the risk becomes a reality. Now, to help you build your own cybersecurity lexicon, here's something to try. Here is your activity. Create a flashcard set for 10 new cybersecurity terms. On one side, the term. On the other, a simple one-sentence definition. When you create these, you'll be actively learning the language of the industry. A card for phishing, for instance, might define it as an attack where a fraudster sends a fake email to trick a person into revealing sensitive information. To conclude, let's check our understanding with a quick fill-in-the-blanks exercise. Here is your prompt. A piece of unpatched software represents a blank. A hacker who knows how to attack that software is a blank. The likelihood that the hacker will attack and cause damage is the blank. The output should clearly show you the relationship. A piece of unpatched software represents a vulnerability. A hacker is a threat. The likelihood of that attack is the risk.
Module 2, Foundational IT Concepts. Welcome to Module 2. To defend the kingdom, you must first understand how it's built, from the layout of the roads to the design of the houses. This module covers essential IT infrastructure knowledge. Lesson 2.1, Windows Fundamentals. Welcome to Lesson 2.1. Your computer's operating system is like the blueprint of a house. Windows, being one of the most common OS in the corporate world, is a house you absolutely must know how to secure. Our objective is to describe the basic architecture and core functionalities of the Windows operating system relevant to security. We will explore key components like the kernel, the file system, and built-in security features. Let's start with the core architecture. Windows separates operations into two modes, kernel mode versus user mode. Kernel mode is the heart of the OS, with unrestricted access to all hardware. User mode is where your applications run, with limited access. This separation is a fundamental security principle. Next is the registry, a central database that stores low-level settings for the OS and applications. Attackers often try to modify it to hide their presence. We also have the NTFS file system and its built-in permissions, which allow you to specify exactly which users can read, write, or execute a file. And finally, Windows has several powerful built-in security features: User Account Control, or UAC, Windows Defender, and BitLocker. User Account Control is the prompt that asks for permission before an app makes changes. Windows Defender is the built-in antivirus. And BitLocker provides full disk encryption. This is a great one to try yourself in your own system. Here is your activity. On your Windows computer, find 3 common security features in the Windows Security Dashboard and write down the purpose of each. When you do this, you'll see Windows Defender for malware protection, the Windows Firewall for network traffic control, and User Account Control for preventing unauthorized changes, all working together to protect your machine. To wrap up, let's consider a scenario. An employee accidentally downloads a suspicious program. When they try to run it, the screen dims and a prompt asks for administrator permission. Here is your prompt. Which Windows security feature is responsible for this action? The output should clearly show you that this is User Account Control, or UAC, in action. Lesson 2.2, Linux Fundamentals. Welcome to Lesson 2.2. If Windows is a pre-built house, Linux is a custom-built home where you have access to all the raw materials. It powers the majority of the world's web servers, and as a security engineer, you must be comfortable using its command line. Our learning objective is to understand basic Linux commands and file system structure pertinent to security operations. We'll cover the file system hierarchy, essential commands, and the critical concept of file permissions.
The Linux file system hierarchy starts from a single root directory, the /. Key directories include /bin for commands, /etc for configuration files, /home for user directories, and /var/log for system logs, which are critical for investigations. You interact with Linux via the command line interface. Essential commands include pwd to show you where you are, ls to list files, and cd to change directory. Cat is used to display the content of a file. A cornerstone of Linux security is its file permissions. Every file and directory has permissions for 3 types of users: the owner, the group, and others, with permissions to read, write, and execute. I encourage you to run these next commands to see the power of this system firsthand. Here is your activity. Use an online Linux terminal. Practice navigating with ls, cd, and pwd. Create a new file with touch my test file. When you run these, you'll experience the direct control the command line offers. You'll move through directories, see your newly created file appear, and get a feel for the basic rhythm of working in a Linux environment. To conclude, let's test this knowledge. You are in a Linux terminal and need to view the contents of a configuration file named sshd-config located in the /etc/ssh/sshd-config directory. Here is your prompt. What single command would you use to display its content on the screen? The answer is the cat command, followed by the full path to the file, cat/etc/ssh/sshd-config. Lesson 2.3, Network Fundamentals. Welcome to Lesson 2.3. A computer network is the digital road system that allows all our devices to communicate. To protect the kingdom, you must understand how these roads are laid out and where to place the guard posts. Our objective is to explain fundamental networking concepts, including network types, devices, and topologies. We will define what a network is, explore LANs and WANs, and identify key hardware. At its core, a network is 2 or more computers connected to share resources. We have 2 main types: the LAN, or local area network, and the WAN, or wide area network. A LAN is a small, local network like in an office. A WAN is a large network connecting LANs together. The most famous WAN is the Internet. Several core devices make this possible. A router is the traffic director, connecting different networks together. A switch is the local intersection, connecting devices within the same LAN. And a firewall is the gatekeeper, a security device that monitors and filters traffic based on security rules. Finally, every device gets a unique IP address, which acts like a street address to ensure data packets are delivered to the right place. Here is a simple diagram you'll want to draw to further solidify this concept. Now for a quick assessment. You have 3 computers and a printer in an office that need to be connected to each other, but not yet to the Internet. Here is your prompt. Which network device would be most appropriate for connecting these devices together on a local area network? The output should clearly show you that the correct device for this job is a switch. Lesson 2.4, the OSI model. Welcome to Lesson 2.4. Sending data across a network is a complex process. The OSI model is a standardized postal system that breaks down this process into 7 manageable layers. Understanding these layers is crucial for diagnosing problems and securing communications. Our objective is to describe the 7 layers of the OSI model and their respective functions. We'll walk through each layer, from the physical cable to the application you interact with. A good mnemonic to remember them is, please do not throw sausage pizza away. Layer 1 is the physical layer, the cables and radio waves. Layer 2 is the data link layer, which handles error-free transfer on the same network using MAC addresses. Layer 3 is the network layer, which routes packets across different networks using IP addresses. This is where the concept of ports lives.
Layer 4 is the transport layer, ensuring reliable delivery using protocols like TCP and UDP. This is where the concept of ports lives. Layer 5 is the session layer, managing connections. Layer 6 is the presentation layer, the translator, that handles things like encryption and data formatting. And finally, Layer 7 is the application layer, which contains the protocols that applications use to communicate, like HTTP for web browsing. This is a great one to try yourself. Think about the process of browsing a website. Here is your activity. Map the common protocols involved in browsing a website to their corresponding OSI layers, specifically HTTP, TCP, and IP. When you run this exercise, the layers become clear. HTTP is an application layer protocol running on top of TCP at the transport layer, which in turn uses IP at the network layer for addressing. To conclude our lesson, let's consider a firewall. It's configured to block all web traffic by blocking port 80, the standard port for HTTP. Here's your prompt. At which layer of the OSI model is this firewall primarily operating? Explain your reasoning. What this reveals is that the firewall is operating at Layer 4, the transport layer. The concept of ports is a function of Layer 4 protocols like TCP and UDP, which manage service-to-service communication.
Module 3, Core Security Concepts and Regulations. Welcome to Module 3. This module introduces the rule book of cybersecurity. The digital world is governed by security frameworks and data protection regulations that every engineer must know and enforce. Lesson 3.1, GDPR. Welcome to Lesson 3.1. Imagine your personal information is your personal property. The General Data Protection Regulation, or GDPR, is a landmark EU law that treats personal data exactly like that. It sets strict rules for any organization in the world that handles the data of EU citizens. Our learning objective is to summarize the key principles and requirements of the GDPR. We'll cover its scope, core principles, and the fundamental rights it grants to individuals. The GDPR applies to any organization, regardless of location, that processes the personal data of individuals in the EU. It is built on several key principles, including purpose limitation, data minimization, and integrity and confidentiality. Data can only be collected for specific purposes. You should only collect what is absolutely necessary, and you must protect it with appropriate security. It also grants individuals powerful rights, including the right to access and the right to erasure, also known as the right to be forgotten. This includes the right to access a copy of your data and the right to erasure, allowing you to have your data deleted. To really solidify this concept, here's a scenario to analyze. Here is your activity. A social media company collects your location data even when you're not using the app and sells it without your clear consent. Which GDPR principles are potentially being violated? The output should clearly show you violations of purpose limitation. They're using the data for a purpose you didn't agree to, and lawfulness, fairness, and transparency, as the collection and sale were not clearly disclosed. Excellent work on the activity. Now for a final assessment. A user in France signs up for a newsletter from a US-based company. They later want the company to delete their name and email address from its database permanently. Here is your prompt. Which specific GDPR right allows them to make this request? The answer, of course, is the right to erasure, or the right to be forgotten. Lesson 3.2, DPDPA. Welcome to Lesson 3.2. Just as the EU established its own digital property rights, many other countries are creating their own rulebooks. India's Digital Personal Data Protection Act, or DPDPA, is a significant recent example. Our objective is to outline the main provisions and implications of the DPDPA in India. We'll discuss its emphasis on consent, the roles it defines, and its breach notification requirements. The DPDPA applies to the processing of digital personal data within India. Its cornerstone is consent.
Personal data can typically only be processed with clear and specific consent from the individual, who is known as the data principal. The company processing the data is the data fiduciary. Key obligations for organizations include providing clear notice about data collection, ensuring data accuracy, and implementing reasonable security safeguards to prevent breaches. This is a direct mandate for security engineering. In the event of a breach, organizations must notify both the Data Protection Board of India and the affected individuals. This is a great one to try yourself to see the global connections in data privacy.